Hello everyone, I'm Anshuman Acharya, a first year PhD student at the Max Planck Institute for Astrophysics in Germany. Today I'll be talking about the project I undertook for my master's thesis at IISER Mohali with Professor Kulinda Pal Singh and Dr. Vinay Kashyap. In this project, we looked at the HD179949 system. The HD179949 star system consists of a sun-like star and a closing Jupiter-mass planet, which orbits around it with a period of just 3 days. Sholnik et al. 2008 found chromospheric X-ray emission, which was correlated with the planetary phase. They concluded that this was indicative of star-planet interactions. However, this correlation was intermittent. Thus, we decided to investigate further by looking at Chandra X-ray data, which looks at the stellar corona. From Chandra, we have 5 observation runs of around 30 kiloseconds each, spread across a wide range of phases, which is quite helpful for us. Next, what we do is we divide the entire data into passbands of different energy ranges. We use the default passbands given by Chandra, as well as we have our own physically motivated passbands where each of the passband is named depending on the dominant excitation in that energy range. Before using the passbands further, we take all of the data together and we perform calibration. We implement the Bayesian blocks algorithm via the SciPy implementation and try to calibrate this for finding the true false alarm probability. For this, firstly, we remove and merge all of the change points which are separated by less than 30 seconds. And then we look into what exactly is the correction factor for getting 1% false alarm probability. We find that it's a factor of 6. So if we input around 6%, then we get a false alarm probability of 1%. This is what we use for finding the light curves for each of the passbands. For example, for the first observation run, for the oxygen passband, we get this light curve, and for the iron passband, we get this. Here we see that there are a lot of different bins of different sizes, which itself is indicative of variability in spectral hardness. Next, we also look into hardness ratios, where, for example, we have again compared oxygen versus iron, and we calculated the reduced chi-square in each case. We found this to be 4.6 in this case and consistently greater than 3 in all cases, which showcases variability in hardness ratios. Lastly, we performed spectral fitting, where we used a two-temperature model for each of the obsides. And here we obtained abundances which are consistent across all these observation runs. And we also got abundance ratios which indicated that we could observe the FIP effect in the system. That is, the low FIP element abundances were enhanced in the corona. The next step of spectral fitting is to obtain the flux parameters using which we can explore the periodicities at the scale of the period of the planet, which is what we plan to do next. In case you have any other questions, feel free to reach out to me and keep a lookout on arXiv as we hope to upload our paper there soon.